Hey guys, so in this set of problems, we're going to be looking at molecules that have elongated pi systems, so p orbitals on adjacent atoms that overlap with each other to form 3, 4, 5 atom pi systems. In this question, we're interested in the properties of this molecule A, and one thing you should keep in mind is that positive and negative charges that are next to double bonds are able to participate in pi systems, right? The p orbital can serve as a container for a lone pair if this is a negative charge, or simply be empty if this is a positive charge, and we then have a contiguous pi system. So in this molecule A, there are 1, 2, 3, 4, 5 atoms that are part of the pi system. Both double bonds and the positive charge are all part of the pi system. How many electrons are here? Well, there are 2 double bonds. That's 2 each from the double bonds, and the positive charge doesn't contribute any electrons to the pi system. So there are 4 pi electrons in A. And finally, this last blank asks us about the number of 2pz coefficients that are equal to 0 in the HOMO of A. And if this seems a little bit non-intuitive to you, the best way to see why the answer is only 1 is to look at the highest occupied molecular orbital in an MO calculation. A little bit later down the line, we'll talk about SHMO, which is a very easy way to calculate pi molecular orbitals. When you run a calculation in SHMO, you'll be looking down on the molecule, so you'll only see 1/2 of the p lobes. So we'll see sort of the top, but we'll only see half of the lobe. So when we look at the HOMO here, you just look at it by clicking on it. Notice that there are 2 lobes of opposite phase and there's a node in the middle. So we would expect 1 node in this orbital, right? 0 nodes in the bottom orbital and 1 in the first one up. Because there are 4 pi electrons, we see that this would have to be the HOMO, and because it's the second level up, we would expect 1 node. Because the molecule is symmetric, right? This molecule is symmetric, that node has to reside on this central atom. For this next problem, we're looking at elongated pi systems and interested in the different properties between beta and alpha carotene. What you should notice about the 2 molecules is that they're nearly identical, except for a difference in the double bond on the end here. So in alpha carotene, it's out of conjugation with the rest of the pi system. In beta carotene, it's in conjugation. So beta carotene has a slightly longer pi system than alpha carotene. So what are the properties of longer pi systems, right? Well, they have smaller HOMO-LUMO gaps, right? So immediately we can go to the second blank and say that the HOMO-LUMO gap in beta carotene, which has the longer pi system, will be lower than the HOMO-LUMO gap in alpha carotene, which has a shorter pi system. The effect on the wavelength has to do with the relationship between energy and wavelength, right? So energy is proportional to frequency and inversely proportional to wavelength. As the wavelength goes down, the wavelength of maximum absorbance will go up. And as we just noted, the difference is best explained by the difference in length between the pi systems. And we saw that beta carotene has the longer contiguous pi system because this double bond on the end here is in conjugation with the long chain of double bonds to the right. From previous lessons, you should be familiar with the ability to look at WebMO results and look at molecular orbital shapes and move back and forth between these. And this problem really just applies that idea to a conjugated pi system. So we're asked to look for the orbital that dictates the electrophilicity, and this should immediately bring to your mind the lowest unoccupied molecular orbital, right? When you're given WebMO results like this, you can immediately find the LUMO by looking for the first orbital in the table that has 0 occupancy. This is the lowest energy orbital that has no electrons within it. So orbital 20 is the one that dictates the electrophilicity of the molecule, or in other words, determines where a nucleophile is most likely to attack. So let's take a look at MO20 just by clicking the button. After a little while, the orbital will load. And we can see from the orbital picture, it's very difficult to tell which atom has the largest lobe, right? Potentially C3, C6, maybe even C5 look like they might have the largest lobes. So we need to go to the raw data, right, and look for the largest number. In this case, this is a pi molecular orbital, right? So we'll have quite a few zeros. This looks like contributions from only one kind of p orbital, probably the 2pz. And so when we go to the raw data, we'll look in orbital 20 and we'll find where the largest number is, right? What we see is that C6, the pz orbital on C6, has the largest coefficient. This immediately tells us, okay, C6 is the most electrophilic atom in this structure. So drawing the structure very quickly, we can map C6 by just typing capital M6. Oh, and we're supposed to map it with a 1. That's the most electrophilic atom in this molecule, and we could tell that very easily just by finding the LUMO and looking for the largest coefficient. This last problem has very simply to do with the number of nodes in the pi molecular orbital. That's it. That's really the only concept you have to have in hand to answer this question, and the knowledge that as the number of nodes increases, the orbital energy increases too. So we can immediately spot the number of nodes in all of these orbitals just for looking at places where the sign changes, right? So look at D as an example. D has 1, 2, 3, 4, 5 nodes in it. We can very quickly see that just by counting the sign changes. But actually another way to figure out the number of nodes, if you're not very keen on this sign change idea, for pi molecular orbitals, a very easy way to do it that actually a student pointed out to me in one of the O-logs is just count the number of distinct regions of color and subtract 1. So in D we have 1, 2, 3, 4, 5, 6 distinct regions of color. Subtract 1 from that and we'll get 5 nodes. On the other hand, in an orbital like B, for instance, we have 1, 2, 3, right? The two reds are really overlapping with each other and connected for 5 distinct regions of color, which should give us 4 nodes. And by counting sign changes, we can see red to blue, there's 1, blue to red 2, red to blue 3, blue to red 4. So there are 4 nodes in B, and the other method produced the same answer. So doing this, we can immediately look at A as the lowest energy orbital. Going up, E is the second lowest with only 1 node. Above that, C has 2 nodes. F has 3. B has 4. And D has 5, and it's the highest energy orbital.